In this video, we're going to discuss fluid conservation laws and Bernoulli's equation. So let's start with volumetric flow rate. So the rate that something flows through a pipe is the change in volume. So the change in that volume is equal to the area times the velocity of that fluid. So let's look at a pipe that, say, a liquid might be flowing through. So there's some area to this pipe, and it's flowing at some velocity. And so that will give you your volumetric flow rate. Okay, and now let's say the pipe gets smaller and the area now goes to this area. Well, if we have a constant volumetric flow rate, then this velocity must get faster because there's less room for the same amount of volume that flows in this first point to flow in the second point. And so that's where we get this equation, where really what we're saying is the volumetric flow rate is constant. So if we have the area and the velocity, and one of those changes, the other variable must change with it. And then finally we have this Bernoulli's equation that basically is energy for fluids, is how you can think about it. So first off, we just have our pressure. So this is our initial pressure at the initial point, and the pressure on this side is just the final pressure, the pressure at the end point. And these, you may notice, look very similar to potential and kinetic energies. So this is kind of like the potential energy of your fluid, and this is like your initial kinetic energy, because we are using this height variable to determine potential energy and the velocity to be the final, or to be the kinetic energy. And so this will be your potential energy final, and this will be your kinetic energy final. And we'll do an example later using this equation. Okay, but let's do an example with changing areas first. So we have water flows through a 0.05 radius pipe at 0.05 meters cubed per second. The pipe then gets bigger to a radius of 0.1 meters. What is the change of velocity? So let's draw out what we're looking at here. So we have the pipe is going through like this originally, and then it gets wider. So we know that the volumetric flow rate is going to be 0.05 meters cubed per second. And so when you're pumping water through this pipe, just because it gets bigger doesn't mean that the same amount of volume isn't going to be going through at any time. Okay, so we have this constant volumetric flow rate. And so now we also know that the radiuses are changing. So the first radius is going to be equal to, and I'll write it as R naught, equals 0.05 meters, and the final radius is 0.1 meters. And so we need to compare these velocities. So let's start by just finding the initial velocity, and we can do the same to find the final, or we can use that other equation. We'll do it both ways and show that it's basically just doing the same thing. So this volumetric flow rate, which I'll call V dot, is equal to the area times this velocity initial. Okay, and this will be the initial area. So to find this area, we can use the radius. So let's rearrange it for the velocity, which is just this volumetric flow rate over the area initial. And so we were given this flow rate of 0.05 meters cubed per second. And the area is just going to be, we're assuming this is a circular pipe since it gave us a radius, is just pi r squared. So we can do pi times the initial radius, which is 0.05 squared, and that's in meters. And so the meters will cancel, and we'll get 6.37 meters per second. And so that's our initial velocity. Now to find our final velocity, we can do this exact same thing, and then we can use the other equation. So I'll do this exact same thing actually, and then show that the other equation works. And it works because we have this constant flow rate. So we can find the V final in the same way of having this constant volumetric flow rate and our area final, which is going to be still 0.05 meters cubed per second over our final area, which is pi r squared, but we want the final rate, which is 0.1 meters. And so when we plug that in, we get 0.016 meters per second. And so if we were to do it the other way, We also know that if we have an area 1 velocity 1 equals the area 2 velocity 2, we could have found this velocity final by doing area 1 velocity 1 over the area 2. And so if we plug those in, we would have pi the initial radius, which is 0.05 squared, times this velocity of 6.37, which we found, over the 0.1 radius squared times pi. And so these pi's cancel, and if we plug it in, we will also get 0.016 meters per second. So we could do it using this equation or using this constant flow rate. And so now we just need to find the change in velocity, which just is the velocity final minus velocity initial. So this velocity is getting smaller since the pipe is getting larger. And so we get a change in velocity of negative 6.35 meters per second. And that'll be our final answer. Alright. Now let's try to derive Torricelli's theorem. And I think Torricelli is how you say his name. Torricelli, if you're watching, I apologize if I said it wrong. So Torricelli's theorem is basically relating the height of a tank to the velocity that a fluid would be flowing out given that there's like a small hole or opening. So we're going to use this Bernoulli's equation here, where we have the pressure initial plus the density gravity initial, or density gravity times height initial, plus 1/2 rho v naught initial, equals this final pressure plus rho g h final plus 1/2 rho v f squared. Okay. And so we can cancel out some variables. First off, the pressure is going to be constant at the input and output because we have this P naught that's pushing down at the top of this tank, and we also have P naught, the same P naught, pushing in on this gap here. So these pressures are going to be equal, so those cancel. Now we also need to set our relative height. So if we set this height equal to 0, we can say that at this point height is 0. So at the final point where the liquid is leaving, the height equals 0, so we can cancel out this final height, and so the initial height is what this h is saying right here. So really we should just say h equals 0 at the exit point, because if we set h to be 0 at the bottom, then we would have to deal with the heights of both of these. But to make it easier, since we're dealing with energy, we can set that to be our reference point. And then finally, the velocity of the fluid up here at the top is going to be about 0, because we're looking at this constant height and this constant velocity, because if we have a big tank and a small opening, compared to this velocity, it's going to be insignificantly small, so it'll be about 0, so we can cancel out this initial velocity. And so now we're just left with the rho g h equals the 1/2 rho vf squared. And so these densities cancel, and we can divide or multiply by 2 to get 2gh equals this velocity squared. And so the velocity of the small opening is the square root of 2gh, and that will be our equation for velocity. So now all we need is the height of the tank relative to the exit point to find what the velocity of the fluid would be exiting. And we use this energy equation to solve for that. So this is the last video for AP Physics 1 for all the units. Feel free to leave your questions down below, and thanks for watching.